3 p.m. Okay, so what we're going to do, I want to do one more image problem and then move on to something totally different for a while, and that'll be kind of refreshing as well. But again, don't forget the salient points. We'll learn to solve partial differential equations as well. So the other image problem, I really couldn't think of a better section title either. You have, as opposed to an infinite plane, you have a sphere, a conducting sphere, and this conducting sphere is grounded. Okay? Meaning it can draw charges. And Griffiths just drew it funny, but now as I don't have space above, I probably see why he did it as well. So he picked this to be the z. See, as I'm writing it, I want to write x. So he picked this to be x-axis. Okay? So just remember that. Because of that, I won't label y and z because it's confusing to think of that as the z-axis. You know, typically I should have drawn that. Okay? All right. And then, so this is a sphere. So it's a conductor. Okay? And a distance a away, a charge q is placed. The question is, what is the electric field and potential everywhere? Once you get the electric field, you can get the potential. This is a conductor. We know half the story. Inside the conductor, the electric field is 0. Therefore, the potential inside the conductor is constant. Right? Because electric field 0, meaning potential is constant. So it is what is actually on the surface of the sphere. Okay, so then the question would be find the potential everywhere, but we're only concerned with the outside at the moment. Find V and E outside for now. We'll do it inside as well. All we have to do, because of the uniqueness theorem, is what? Write a potential such that it satisfies del squared V equals minus, what is it? Q over epsilon naught delta Z minus A. Right? Well, that is almost easy. And the second condition that is required, V at because a conductor is an equipotential surface. So these are the requirements. And don't forget the useful but abstract relationship del squared of 1 over r is what? Minus 4 pi delta yeah?
You also need to consider the infinity going to 0, or
it'll end up being that. Yeah, infinity going to 0. Again, whenever you have compact charges, you know, a couple of charges here, a massive star with charges inside it, around it, infinitely far away, you don't see the star. It's only when the entire universe is filled with stuff like an infinite plate of conductor, which is sort of ridiculous. The only real circumstance when you consider the entire universe filled with stuff is a course by itself. It's cosmology. None of these rules would apply, right? We have to come up with new techniques to find solutions. Okay, now I know how to satisfy this part. It is k q over r, where at any point r, if I want to know the field, let me write this over here. I can call this let me call this requirement 1. Here, r is equal to r minus a c hat. I always write it in this convenient order. Remember, that is not easy to see very quickly, but it is. This plus this is that. So a times z plus script r is little r. So when you do this, it's this minus that. That's where it comes from, okay? Yeah. Correct? It satisfies one, but it doesn't satisfy the other. And from uniqueness theorem, we know that all we have to do is write something whose Laplacian is 0. The Laplacian should not be affected by it because it's already fixed, that's taken care of. But when you add it up on the sphere, the potential becomes a constant. So how do you do it? It's done by simple geometry. Let me write the result first. You invent a virtual charge. We call it Q prime. There's no charge there, okay? And this distance, you call it B. And this distance, or this vector here, I'm going to call it R prime. Look, this is script R. This is script R prime. And I'm going to write this as K Q prime. I haven't told you everything yet. Where script R is R minus B C. Well, that's fine. You will say, well, what is my virtual charge and how far is it away from the center? So I should tell you what, so this is a guess. It has to be negative. If you bring a positive charge to a conductor, it's going to attract negative charge. But it doesn't attract equal amounts. You'll see why. It is this ratio. I want to, let me just make sure I'm getting the numbers correct. Yeah. And how far away from the center do I place it? And at this point, you're saying, yeah, if you say so. Where did you get these numbers from? Well, somebody called it Q prime and B and solved it such that when R equals big R, potential turns out to be a constant, and then they backwrote the answer. So when you see the finished product, you don't see all the mess that went in the calculation. But I should clarify this to you. So first of all, if I add both of these, is one still satisfied? Yes, because this is never zero outside the sphere. So there is no additional charge that is created. What is the only thing left to verify? It's a constant. Need to show that 2, and I'm blocking the projector here. What I'm writing here is 2 is satisfied. When I say 2, I mean this requirement. Yep. I'm conjured it up. What I'm saying is, if I place a charge Q prime, well, what is Q prime? That. At a distance, B away from the center. Well, what's B? That number. Then, this is not affected, which is true. But the claim is, just doing that will fix this requirement. So, Poisson equation is satisfied, boundary conditions are satisfied, uniqueness theorem tells you that you have the only potential. So follow the argument with me. So, gosh, I'm out of space. Space I know how to create. Time, however, goes in one direction. So let me calculate this very quickly. Let me write the squared, and then I can take the square root. Well, just by looking at what R is, it's R minus AZ dot R minus AZ hat. Foil it out for me, Travis. What's the first term I'm going to get? R squared, good. Then what am I going to get? Plus, not A squared, Z squared. Well, what is Z squared? This is not multiplication. So what is? Good. No. Z dot Z is 1. And then you're going to have this dot this and this dot this. They're exactly the same term. So I get minus 2a z hat dot r hat, or r hat dot z hat. Correct? But r hat dot z hat is exactly cosine theta, where this angle is theta. So this is r squared minus 2, hold on, 2a r cosine theta plus e squared. Nope, I didn't get very good. And that's why there's r over here. The magnitude of r vector, which is little r times r hat. But r hat dot z hat is cosine theta. Now, this is r hat. This is z hat. These are parallel lines, so it's cosine theta. Yes?
You went from sine to square.
Well, because this is just the square root of that. I could have put the square root in the first place. So r prime squared. What is that going to be? What is the only thing that changes? A becomes a B. And therefore, I'm going to continue here. The potential becomes, and I'm going to factor out a KQ. And tell me, what am I doing over here? I'm just going to B cosine theta plus B squared. I didn't do much. Yeah? What did I do? I just factored out the Q. Now, what I'm going to do is evaluate this at, I'll need as much space as I can if I have to write big, or if I say it like our former president, if I write bigly, I get KQ 1 over r squared minus 2ar cosine theta plus a squared, and I'm just going to write it as 1/2 minus r over a r squared minus 2r r squared over a cosine theta plus r to the 4th over a squared. Is that correct? Yeah? And then I'm going to take this into this. So what I can do is and then I square it and I multiply. So I get KQ a squared over r squared. Okay, watch it. Copy this down if you're writing it down. I can correct? Check out these two terms, just in backwards order. R squared, a squared, a squared. So that works. The rest of the image problem is part of a homework that I would actually like for you to go through. They'll ask you to compute induced charge and compute the energy of the problem. I would like for you to go through both of that, exactly like we did for the infinite conductor. That's, if you have any questions, let me know. How would you find the surface charge density? The normal derivative, right? Yeah. In energy, there's an integral formula. So this is the other image problem. You know what? I drew it this way. I didn't make it very clear. How do you know B is less than R? I know B is less than R because R squared over A can be written as that. And A is bigger than R, so this number is less than 1. When you take a number less than 1 and multiply by R, you get a number less than R. So B is in fact inside the circle. Yeah? But what is odd about this problem? Q prime is not equal to negative Q. Yeah? Again, it brings a negative charge, but less than the magnitude of Q. But that's simply how the geometry works out. So what was done? People who, in high school geometry, we draw all these circles and surfaces and the old-fashioned analytical geometry. So somebody had the insight saying, wait a minute, I remember you can get these constant spheres from a high school analytic geometry technique, and they called it maybe Q prime and B, and they cranked it out and reverse solved it. What must be Q prime and B to fix this problem? So now you can see how the story was written.
What is the sphere being rounded effect?
Oh, potential equals 0.
So if it was conducting and wasn't?
If it, that's not so easy to solve.
So for now, if it's conducting, it's going to be grounded.
For these image problems. Yeah. Now, you might say, now, don't hold me to this. It's a very good question. If it's not grounded, if it still has to be an equipotential, then you could presumably add a constant, but then there's a problem with that. Because when you do E dot dA over here, you're going to get a Q prime. And the question is, where did that Q prime come from? If it's grounded, it can bring that Q prime. Yeah. There may be a clever way out of it. I'm not thinking of that at the moment. But yeah, if you move but one piece, you have to see what falls apart, just all the checks and balances. Yeah. Good. Any questions? Image problem is both easy and difficult. Difficult, you have to do the whole calculation. It's easy because it's done. You can't do any more with it. Yeah. 128. I think that's where they.
29 is the chromosome.
Yeah. And now comes the fun part. I could call this section partial differential equations, but that would make it sound like it's a math course. And we're not studying all types of partial differential equations. We're going to study ones that are relevant to us. In particular, Laplace's equation. Because we are able, just by putting a conductor, sort of a waveguide, we're able to construct surfaces with constant potentials, maybe. And then the question is, what is the potential everywhere inside? It can be different constants. So I could have some height to be 10 volts. This could be 9 volts. And this could be going from 9 to 10, just increasing. On one side, I can put conducting surfaces. And so the potential inside cannot be constant because it has to go from 9 to 10. Well, what is the potential? It can be easily solved. So this is fun. It harkens back to just calculus, and that to simple calculus. So you'll enjoy doing this. And let me see what section. It calls it separation of variables. But maybe I should say some solutions to the Laplace equation. And the first technique we're going to do this in several coordinate systems. In fact, in this book, we're going to do it in Cartesian and spherical coordinate system. If you take a graduate E&M course, they'll do it in cylindrical coordinate system as well. But that's just more math. It's not something we need for the problems that we're trying to do. Okay, so what is Laplace's equation to begin with? So, in this section, we're going to use Cartesian coordinate system. In Cartesian coordinate system, what we need to do is solve for and so, to describe the general method, let's do a specific problem. As the boundary conditions change, you will be using literally the same kind of problems, same kind of technique. But here, everything depends on the boundary condition. And I need to draw a figure. So you have two infinite conducting planes. When I do this, that's what I mean by infinite. It's not a finite edge. I'm just drawing a portion of it, and I'll give you different perspectives of what I'm drawing. And also look at the textbook. That's not a very good diagram. But let me have something more definite in mind. So, And again, Griffiths uses a useful coordinate system. I'll show you why. This is Z, this is X, this is Y. So let me give you another perspective. Look at the diagram in the textbook. So what you have is, this is my Y-axis, and this is Y equal to 0. This entire XZ plane is an infinite conducting plane. Yeah? This is Y equals A. Yeah? And they're both conducting surfaces. And because, oh, you know what? Let me make this clear. I can make this straight because all conducting materials end on the YZ plane. There's nothing over here. Okay? This is also a conductor. So what you're seeing in that diagram, conductor number 1, conductor number 2, and this goes on forever, and it comes out forever as well, and you have a third conductor, you see it? That is the diagram. So the entire half plane is a conducting plane. This entire half plane is a conducting plane. And between these two conducting planes, there's an infinite strip of conductors. Okay? What we're interested in is finding the potential here. But here, the potential on this surface is set to be 0. Same thing over here is set to be 0. And setting it to be something else is simply a different problem for me to assign. Yeah? And over here, at the moment, we can call it, it is V0 of Y. So, sorry, this is not a conducting plane. The potential is changing. It is dependent only on Y. So blue is conducting. So conducting plane, conducting plane. Here, the potential is slowly increasing by some mechanism, maybe by charges placed along the strip. This is an insulating surface, such that the potential depends on the height from the ground. And so here, it's that's given to you. We'll pick a definite choice, but only on this boundary, the potential here is of some function V0 of Y. And the goal of the question is, the question itself is, what is the potential everywhere? Before we embark on the math part, which is almost trivial, but long, is the problem clear? Yeah.
So are we saying that because of this potential that exists in that space,
Yeah.
that's what's going to, and so we're given this and some potential here together, that's what produces 0, 0 on top and bottom?
No, the top and bottom, it's easy. It's a grounded conductor. Here you're putting some insulating material with charges to create this sort of a potential.
Okay.
Yeah.
Okay. So as a result of this
Yeah.
0, 0, we now.
You have an inside potential.
Okay, got it.
Yeah. Something that it does something in between. Yeah. Okay. To begin with, your potential in general depends on x, y, and z in Cartesian coordinates. But in this problem, why would it depend on z? It's this entire plane over here, and you have an entire plane over here, and then the strip in between that goes through the entire z. So at no point in z value, life looks differently to you. Yeah? So there's a symmetry along the z-axis. And from here comes the actual section title according to Griffiths. So let's, as a guess, we have no idea how to solve this. But we're going to guess something and then see what pans out. Yeah? We're going to say that the solution is separated in variables. That means there's one function, x, which is only a function of little x, and another function, big Y, which is only a function of little y. So this is a guess in, I don't know the exact meaning of the word ansatz, but the term is used to mean precisely guess. So we're guessing that the solution can be written with the variables separated. Not all functions can be separated. I mean, I can think of many functions that cannot be separated like that. But that's, so we may be restricting ourselves in the beginning. But you know what? We have no better way to proceed. Okay? And I'm going to take this and put it in here. Tell me if this makes sense to you. Oops. Because the x derivatives do not see y, the y derivatives do not see big X. X derivatives do not see big Y. Y derivatives do not see big X. So what I'm saying here is there's a function big X, capital X, which is a function of our coordinate variable X. It's a function Y. Yeah. So this is the only conceptual part of the problem in terms of the setup. The rest follows very quickly. Is this clear?
I'm sorry, could you just kind of re-explain that just a little bit?
Well, let me do this first term. Well, you know what? It's not. Why don't I just? We're not trying to save that much space. Oops. Right. Do I need to take the z derivative? Z is totally out of the picture, right? Now, here I'm taking derivative with respect to x. This big X is a function of x. This big Y is a function of what? Little y. So when you take the derivative with respect to x, are you taking the derivative of y? And yeah, because when you take partial derivative, the other variable is treated as a constant. So I can state this. Gosh, on Monday when I do this problem, I'm not going to draw this picture. That's not entirely too bad, but it took me a while to construct this. So remember this, commit to your memory before class, look it up. So that equation means how did I get that? I divided by x times y. Here y and y will cancel, I'll get x. And the second one, x and x will cancel, I'll get y. And therefore, I get a curious equation. And tell me, what's curious about this? Oops. What is curious about this equation? How can this even be? Let big X describe the number of pennies in a pond, or money in a pond. Let Y describe the sweetness of a persimmon fruit. You're saying some differential equation about pennies in a pond is equal to negative the sweetness of persimmon. X and Y are not, they're independent variables. The only way, correct. Thank you. The only way this can happen, I want you to ponder this, is if there's no other way. Because this can vary independently, this can vary independently. You cannot have two functions of entirely disconnected objects equal to each other. Unless they never take on but a single value. Because the moment they change, they can change independently. And so these are the governing equations to solve our partial differential equation. By the technique of separation of partial differential, separation of variables, we have converted a second order partial differential equation to two first order partial differential equations. Sorry, first order ordinary differential equations. And if you're wondering what do I mean by differential equation, it means an equation with derivatives in there.
You're saying when you said ordinary, we can convert the partials to just these.
That's it. Yeah, this has got no, so I'll write it that way next time. Yeah, what Martin is saying is, I'm done with this nonsense of partial derivatives. That's what it is. Yeah? So 1 for the price of 2. You have to solve 2 equations, but gosh, they don't talk to each other. They're completely uncluttered. They're just ordinary derivatives. So it's rather a powerful technique. So once again,